Thank you. Thank you. So yeah, as already mentioned, I'm Rustam Balafendiev of ITMO University in St. Petersburg, and today I'll be talking about how metamaterials, specifically wire metamaterials, can be used in search for axions. So to start with, the definition for metamaterial is basically an artificial electromagnetic material. And they typically consist of these unit cells or molecules, which allow us to design some specific parameters or specific features in materials which are not achievable in natural materials. Depending on the scale of this molecule or unit cell, metamaterials can be realized in various ranges of frequencies in optics, in radio, and so on. So specifically today, I'll be talking about the class of metamaterials called artificial dielectrics, which can be characterized by the fact that the unit cell is much smaller than the wavelength, which allows us to treat the metamaterial as a homogenized medium and describe it in terms of material parameters, such as permittivity. And these are actually the first class of metamaterials which have been studied by Koch as far back as 1950s. So why metamaterials are included in this category? And the interesting point about wire metamaterials is that they have a behavior that is very close to plasma. So they have this plasma frequency, which gives the permittivity, the dependence, similar to that of metals, for instance, where below this plasma frequency, the permittivity is negative, and above the plasma frequency starts to slowly approach unity, like this. So this graph right here is unitless, but typically for wire metamaterials, the range of this plasma frequency would be somewhere around hundreds of megahertz, gigahertz, possibly terahertz if we're talking about nanoscale metamaterials based on aluminum and stuff. And yeah, wire metamaterial is also something that's been known since the middle of the last century, and has been studied by Brown as far as 1960s. Previously, though, yeah, but previously it was mostly studied for its applications in subwave imaging and what's the correct term for this? Sorry. Subwave imaging and like that. However, the application that I'm talking about right now is quite novel. So, as mentioned previously, the interesting point about metamaterials is that the permittivity can be engineered based on the parameters of the unit cell, of this molecule-like thing that our material ends up consisting of. And in the wire metamaterial, this unit cell ends up being a single wire. So depending on the period of this lattice and the radius, we can very easily choose the plasma frequency of our wire metamaterial and essentially choose the permittivity at a specific frequency. And the reason this is interesting is that this can be applied to cavity horoscopes. In traditional cavity horoscopes, we are very rigidly constrained by the dimensions of the horoscope. So based on the volume, we are like, unless some specific tuning scheme is used, like rotating rod or something, it's very difficult to extend the principle of cavity horoscopes to tens of gigahertz. because the size of the cavity itself becomes very small and the sensitivity falls as well. However, by using something like a plasma and by utilizing this property of the permittivity being between 0 and unity, we can essentially stretch out the wavelength of plasmon in the wire metamaterial to match the wavelength of the axion. And what this allows to do is essentially by filling the cavity with this wire metamaterial, we can somewhat decouple the size of the cavity from the frequency at which it operates on. Furthermore, unlike normal plasma, our artificial plasma is much more suited for operation in horoscopes because artificial plasma such as wire metamaterial is stable, is very easily engineered in terms of plasma frequency, as I mentioned, and doesn't have any problem operating at cryogenic temperatures and in large magnetic fields. And as Matthew Wilson, who proposed this idea initially, says in his paper, it breaks this tyranny of the volume of the cavity being intrinsically linked to the operating frequency by effectively reducing the electrical size of the resonator. So if you now look at something very simple, like a cube filled with this wire metamaterial, for instance, spaced out with this period A and having radius R, this is essentially the distribution of the electric field that ends up arising in this cube. And as you can see, it's the same as in a normal cavity. So what essentially ends up happening is we just take the fundamental mode of the cavity and we bump it up in frequency by the plasma frequency of the wire metamaterial. So in that terms, things end up being very intuitive. Obviously, there is some change in how the magnetic field looks in the cavity because of the local field of each wire, because the whole behavior of artificial plasma does arise because of inductive coupling, inductive interactions between wires. However, if we average out across all the unit cells, we can see that in terms of magnetic field, the overall field distribution is also very similar to a field distribution of fundamental mode of the cavity. So the next question that can be asked here is that, well, you took your well-working microwave cavity, which had this quality factor of about 10,000 or so, and for some reason you filled it with a bunch of metallic wires. Wouldn't that negatively impact the quality factor and the sensitivity? Wouldn't the loss of sensitivity because of this raised surface losses be more detrimental than any gain in volume that you can achieve? And to check that, we initially derived the formula for the quality factor analytically, and it ends up just basically being 1 over the imaginary value of permittivity, at least in the limit of a very large cavity. As you go from a small cavity to something infinitely large, but just in theory, you approach the same behavior as an infinite lattice of wires, as an infinite metamaterial. And the losses in the cavity ends up looking very close as well. So this is how it looks if graphed out. So this is what I was talking about. And the behavior you can see here is the losses in the wires are significantly higher than the losses on the walls of the cavity. And as we increase the volume of our cavity, of our resonator, the losses in the wires tend to dominate more and more over losses in the cavity. However, they also tend to reach some plateauing value, tend to reach some constant, which is typically around several thousand. So we do lose like an order of magnitude compared to traditional cavities, but this does bode well in terms of sensitivity observes. Yeah. So yeah, I will show this in a second. But this is where here essentially cavity is being stretched in the transversal direction regarding our yeah. So the infinite lattice this yeah, so the infinite lattice is the quality factor derived like this. So without this term in the bottom of our equation on the bottom. And for numerical values, essentially I gained the same value by just using periodical boundary conditions. Okay, yeah. So in terms of your question, that will be a bit later actually, yeah. Yeah, sure. Uh-huh. Oh, this is just to mention that it's omega and not have to not forget the 2p. You're not talking about difference between all the wires? No. So here what we consider is the fundamental mode of the cavity, where the wave vector only has components in the transversal directions, essentially. So if I go a couple of slides further, just skipping over that because this might be useful to mention now. You can see that the distribution of the field in the cavity, it's the same in the direction of the wires. So if we ignore any contribution from adding our antennas, our probes, the entire behavior of this cavity of this limited Y medium can be seen by just modeling a 2D slice. Because as we go along the wires, along the Z direction, so to say, you just get the same distribution. Yep. Okay, so yeah, and another thing that we found out through this analytical investigation is that even though as we go to thicker wires, the theory becomes less and less applicable because it needs the wires to be significantly smaller than the wavelength and the period to work exactly. We can scope out that it seems that using thicker wires is also beneficial for the quality factor, and that way it could be raised even higher. For that figure right here, I used the ratio of radius to the period of 1/10. So, and that's pretty much at the edge of applicability of numerical of analytical formulas that I shown previously. Yeah, so the next step was obviously to try and prove that experimentally. And here are some of the results. Can just skip to the next slide, I think. Yeah, so we aren't able to go quite to the numerically predicted value of the quality factor, but we are able to show that this this idea that the quality factor doesn't go down more than an order of magnitude compared to an empty cavity does seem to hold. So we are able to get a quality factor of an order of 1,000. And that seemed consistent between the two prototypes that we did at ITMO and at Stockholm University, where another part of the Alpha Consortium is also based. Okay, so as I mentioned previously, a very interesting thing about wire metamaterials is that they have this intrinsic capability of being tuned very easily by just changing the either radius, which sounds less achievable, or the period, which can be done as simply as just essentially stretching the whole thing as an accordion or something. But if you do that, you have to somehow change the volume of the cavity as well, which sounds also quite hard to achieve from an engineering perspective. So what we ended up doing instead is something like this. Basically splitting a single lattice of a wire medium into two sublattices, and then moving one in relation to the other. So if I now characterize the two sublattices as having these periods of A and B and being moved away from each other by this vector delta, the dependence on the plasma frequency on this vector looks something like this. So the maximum of the plasma frequency is in the center on all of this, and here the four graphs are different ratios of period to the radius of the wires. So A to R0 equal 10T is something, once again, very close to the edge of applicability of our analytic theory, and A to R0 equals 200 is something that's supposed to work very well. And to the left are the case where the sublattices are square, and to the right is the case where the sublattice is twice stretched along the y direction. So this is actually what you would get if you start with a square lattice and then divide that into two rectangular sublattices. And as you can see here, most of the tuning can be done by just moving along one direction, along y direction, and any movement along the x direction doesn't change the frequency all that much. So if visualized, it looks something like this. So those are the wires inside the cavity with the electric field superimposed, and the way the frequency changes alongside it. So this right here is no longer the plasma frequency, this is the resonance frequency of the cavity, at least the 2D slice of it. As I mentioned previously, this is supposed to characterize the entire cavity as well. Yeah, and the reason we can do it partially is because the losses in the wires are so much higher than the losses in the at the walls. So the contribution of the top and bottom wall doesn't end up contributing as much. Yep, and this is the same contour as I shown right here, essentially. Okay. So yeah, I think this is all for today. Quite a shorter talk, possibly, but for more information, you can check out the white paper that we released recently in Physical Review D on this, using this QR code, for instance. And if you have any questions, please do go on ahead. Yeah. Yeah. I forgot to mention that. Yeah, for this is covered in the white paper as well. There are some plans to do it, but so far they are just plans. There are some estimations of how much it could improve things, but yeah, so far those are only that estimations. Not rest. Yes. Sorry? So far, we just looked at the quality factor at the room temperatures. Yeah, and we are yet to both go to the cryogenic temperatures and look at how this whole thing would interact with the magnetic field. Luckily enough, our colleagues in the USA are working towards establishing some working relations with people with magnets and cryostats. Okay. Any further questions? Yeah. So I think the first practical limitation you would run into is the bore of magnet. There is a limitation, I think, but it's quite hard to reach. It's like you can't go to infinity exactly, but for all intents and purposes, there is little particle limitation into how far it can go. Initially, there was a concern before we looked into the quality factor that maybe the losses would be too high to treat the excitation as exciting the entire cavity. But since the quality factor is in the order of thousands, we seem to be able to treat the photon axion conversion as exciting the entire cavity, and that whole scenario doesn't seem to apply. So from that point of view, it also seems to be kind of almost limitless.
About the precision of the mechanical tolerances aligned between wires, stuff like that.
So this whole thing, as you can see from the tuning, in a sense, it works if you move the wires in the transversal directions a bit. However, it does end up very sensitive into longitudinal alignment. So something that I didn't cover here because I'm still looking into it and it's still a work in progress, but this whole assumption, like limiting ourselves to look into TM mode only works if we have a structure that's completely homogeneous in the Z direction. As soon as we have any tilt in the wires, any tilt in the probes, or some unhomogeneity in the walls or something, we start encountering both TE modes and also TEM modes, which are something introduced by the presence of a wire medium. And both of these can be detrimental into how much of this tuning range we can use actually. So yeah, but in terms of transversal movement, there's quite a bit of leeway, as it seems.
These constraints do not scale with volume of the prototype? Like being harder for larger volume?
I think from the practical standpoint, it would be harder to ensure that there's no bending or anything. Just from that standpoint, there's probably some scaling as well. Yeah. So far, our prototypes have been quite small. We are yet to go to these larger scales where they would become more prominent. But I would expect it would be a factor. Yes? Mm-hmm. Yeah. Mm-hmm. You're talking about TE modes, for instance? Yes, yes. Yeah. So that is a problem, and that's why any inhomogeneities are so detrimental, because now that we've pushed the fundamental frequency of the cavity up for the Z direction. I haven't put that on the slide, but essentially, if you write out the matrix of the permittivity for this wire medium, it has this epsilon like non-trivial epsilon, I don't know how to mention that, but something between 0 and unity only for the z direction, and for the other two directions, it's still 1. It's still air or whatever other thing you put between the wires. So as soon as there's some propagation in the transversal direction, the cavity works the same as it would if it were filled by air. So that high in frequency, you have a lot of TE modes of these other modes that are obstructing the operation. Yeah. So luckily so far, like this depends on how much inhomogeneity you have in the volume, and we don't seem to couple as much if we introduce some inhomogeneities at the walls, which is something we have to do if we add tuning to this whole system. For TEM modes, yeah, it seems to be a bit more difficult to ensure absence of coupling, unfortunately. But yeah, I expect Carl to maybe talk about this in his talk at the conference week, in a week, because the part of the work that has to do with tuning has been done partially in collaboration with UC Berkeley. So, and we're currently working on a publication which will cover that in more detail, hopefully. Okay, so any other questions? Oh, yeah, sure. So, so far in my simulations, I've just been using these simple monopole antennas. Here you can see two because it was easier to get the quality factor out if you do transmission measurement rather than just reflection. But yeah, the plan, the simplest thing to do is just to put this dipole antenna at either bottom or top wall where the wires are terminated. But theoretically, you can also use some magnetic loops to couple to a magnetic field at the sides. It's just that this, as I mentioned, would introduce some inhomogeneity to the volume and end up coupling to inducing coupling to the other modes of the cavity, unfortunately, which it doesn't happen if we just use something that is also aligned along the Z direction. Yeah.
You mentioned the beginning.
Yes, this is something that has been done for this for the purposes of subwave imaging, for instance. As far as I remember, I don't quite remember the exact manufacturing procedure, but there are already a ton of papers that deal with using wire metamaterial at terahertz frequencies at near infrared. To an extent, yes. So yeah, theoretically, this whole concept can be extended to terahertz as well, but personally, my expertise lies in the microwave range, so I'm not as qualified to talk about it, unfortunately. Yeah.